here called Omega C. If you, you can find it in GitHub. And so this is a particular iteration of it that allows us to answer counterfactual queries. And so I read this paper a while ago. I'm rereading it again recently, and really trying to kind of understand at a theoretical level the kinds of abstractions that you can build here. And I made some progress, but I'm hoping other people. Is Jeremy on the call? Jeremy, are you here? Not yet. Oh, that's too bad. I'm hoping some other folks have some other opinions, but actually, let me Slack Jeremy real quick.
Can I ask a naive question if we haven't started yet?
Yeah, go ahead.
Is a counterfactual kind of just like two do's in a row? Subtracting two do's.
Yeah. Okay. You know what? I'll go and disembed. So counterfactual. That word is extremely overloaded across communities, particularly in the machine learning community, where it's basically something clever you say if you want to try and get a paper published. But like, so in machine learning, the way I've seen people say counterfactual is like they'll have some kind of data point, and maybe they're using they have some kind of latent space model. Like, so they have some kind of encoding vector for some observed variable, an image or natural language. And they kind of map it back to a continuous latent space. And then they'll ask like, all right, well, maybe there's some kind of decision boundary for classification in this latent space. And so like, let me define a distance metric in the latent space, and let me find like the closest value in the latent space that crosses the decision boundary, and then kind of project that back to a new data point, and that new data point is the counterfactual example. And so like you can use that in adversarial machine learning, where you're trying to say like, all right, here's something that gives me the right classification. What's the closest image I can get that would give me a wrong classification, and then look at compare those two images, the so-called true image and the counterfactual image, and see like, do these two images look alike? Are they distinguishable from the human eye? Can I train some kind of adversarial discriminator to discriminate the true? Can I improve my algorithm by trying to discriminate between the counterfactual example and the true example? And so that's kind of being loosey-goosey about the definition of counterfactuals from the causal inference community. In the causal inference community, you have like the kind of potential outcomes people who define counterfactual in a kind of, they would use a clinical setting. So say, or a marketing setting. So in the clinic, you'd say, I gave this person a treatment and they had this outcome, right? And the question is, if I'd given them a different treatment, what outcome would they have gotten? And so the way they treat that is they say like, all right, well, we have two variables here, the outcome that they got and the outcome that they would have gotten under a different treatment. And that outcome that they would have gotten under a different treatment they call that the counterfactual outcome. Now, what we're dealing with here is a Judea-Pearl style definition of counterfactuals, which you might call structural counterfactuals or twin world counterfactuals. And so this is it's easier to think about this in a kind of generative setting. So kind of, let me not use that as an example, but if I said, all right, the example I just gave would be, all right, I have a generative model of exposure and outcome. I do some intervention, maybe that it kind of fixes the exposure for this person, but you don't need an intervention in that initial case. But yeah, so I gave this person a treatment and they got some kind of outcome. Conditional on that predicts the outcome they would have gotten under a different treatment. And so the difference between that potential outcomes definition and this with this so-called twin world definition is that in the potential outcomes definition is kind of like you just have two different random variables, or or if you're being kind of frequentist, you have two different parameters that you're trying to estimate. In this case, you're using the observed outcome to predict the outcome in the twin world. So you can think of it like science fiction, right? Like, so like, you know, there was some choice where I have given this person that treatment or the alternative treatment. And at the moment I made that choice, the universe split into two parallel universes. And I live in this universe and I want to know what happened in that universe. And so I have some kind of model, because I couldn't do this without a model, but I have some kind of model that allows me to kind of start from what I observed in this universe and kind of rewind the clock, use kind of inductive inference to rewind this to the initial conditions that happened right when I made that choice, and then switch the choice using an intervention. And then from those same initial conditions, start replaying out what happened, what I kind of simulating that parallel universe, and then predicting, kind of using forward simulation, what happened there. And so what's the difference between that potential outcomes approach and this Pearlian approach is that in the potential outcome approach is two different parameters, two different estimations. Well, one you observe, so you don't need to estimate anything. The other one, you're kind of using some estimation techniques. In this case, we are, for an individual case, we are, there's an information connection through the model. Again, this can't happen without a model. Through the model that kind of does inductive inference to the initial conditions of the initial choice, and then forward simulation in the other case. And so like this paper uses some dynamic systems. So they use a Log-Volterra model, they use a pendulum model, and I actually think dynamic systems are a great way to describe this, because if you're, say familiar with ODEs, that's a great way of thinking about it. Like we have, an ODE takes some initial conditions, you plug it into some dynamic model of the world that you're modeling, the domain that you're modeling, and then and then it kind of generates a trajectory. And then you observe the outcome of the trajectory, or maybe you observe the entire trajectory itself. And then what you do there is you say like, all right, well, rewind that trajectory, try to infer what the initial conditions were, and then change the model somehow, and then play the model forward again under these new conditions, and see what, and that would tell you what trajectory you would have gotten.
That's super helpful. Thank you.
Yeah, and so like if without, and the thing to keep in mind there is for that to work, you need the ODE model, the potential or the stochastic differential equation model or whatever, or the agent model, whatever model you're using. Without the model, if you're just trying to use statistics, you can do the estimation for averaged across populations, but not for an individual trajectory. You can do it for an average trajectories, but not for an individual trajectory. I hope that makes sense. And then the other thing that, and I'm kind of hearing potential outcomes people yell at me in my head right now, but what they would say is that, well, you can condition on all of the variables. So you can do kind of conditional treatment effects is what they call it, but you can kind of condition on variables that matter and kind of narrow it down to a subpopulation. And in theory, you could keep conditioning until you got to like the one individual. But of course, then you get, that leads to problems with the probability distribution. The probability distribution becomes degenerate. Also, of course, the more things you condition on, the more expensive the algorithm and the more data you need. The argument kind of, so the way I kind of approach this paper is I try to, he uses a bunch of semantics in Julia, or he uses a bunch of Julia code and then does a whole bunch of kind of proofs using lambda calculus, which I'm kind of sketchy on, but I was really trying to come out like, all right, what is the core contribution here? What, from a programming standpoint, what kind of new abstractions are we developing? And so let me just dive in here. So his argument here is that conditioning alone is insufficient to express counterfactuals. So what's counterfactual? It represents a what-if inference. His core argument is that generic mechanisms for counterfactual inferences need additional abstractions beyond conventional probabilistic programming. So we're in probabilistic programming land. We want to, probabilistic programming, we can do, obviously we can condition on things, we can condition on evidence and predict the values of variables, condition on other variables. But we need to go beyond conditioning we can also do interventions by setting variables to specific intervention values and kind of doing forward propagation from there. But we need something more if we're going to do the counterfactual queries. So what's a counterfactual? Given X, what would Y have been had Z been different? In a case, and what's important here is that Z can invalidate the truth of X. So what does that mean? Invalidate the truth of X. So given a drug treatment was not effective on patient X, what would it have been had we given the stronger dosage? So that stronger dosage invalidates the truth of the drug treatment that I actually gave them. So if I said I gave them 200 milligrams, what would have happened had I given them 300 milligrams? Well, I can't. The problem, if I just want to do conditioning, I say, all right, conditional on 200 milligrams, and then I condition on 300 milligrams. So those two things are in conflict, right? So I need something beyond conditioning. If I say condition on 200 milligrams and do an intervention on 300 milligrams, well, the conditioning statement and the intervention statement are also in conflict. So he's arguing that, so that's what Z can invalidate truth of X means. But of course, this is something that we really want to think about. Like, say we're doing, personally, I think one of the more interesting applications of counterfactual reasoning is in reinforcement learning, where you might have an agent that says, I applied this policy and got this reward 3 steps ago. Had I applied a different policy, I would have this different reward or this different cumulative reward right now. So in the future, and that reward is better. So in the future, when I encounter a situation that's similar to that, I'm going to use a new policy. And that's kind of how humans make decisions in life, right? We minimize counterfactual regret. Like, I did that and I got this bad results, so I'm not going to do things like that again. So the question that comes here is that, so if you're taking my workshop now and we haven't gotten the counterfactuals yet, we'll see that we can model counterfactuals using a causal generative model, namely something called a structural causal model. And the question becomes like, well, if we have structural causal models, kind of causal generative model, why would we want to use probabilistic programming? And the argument here is that probabilistic programming is more expressive. One thing you can do is you have an unbounded number of variables, and that number of variables can vary as the program continues to execute. And so, I extracted this example from other parts of the literature, but you would say like, all right, is there a counterfactual query where we might want unboundedness? And so, so we can do that with like first order logic. Think of a military application. The enemy fired missiles and we detected 10 of those missiles on radar. Would we have detected all the missiles if they had fired? Let's assume that the enemy fired 10 missiles. And you detected all 10 of them. Question is now, would we have detected all 10 of the missiles or all of the missiles if they had fired more than 20? Right, and so now you need an open-ended number of missiles with a lower bound. And but that's the kind of, I hope the impact of that question is like, yeah, okay, this could be, if you're Israel and Hamas is shooting missiles into Israel, then maybe you're trying to figure out, that your radar detection system it's an estimate of the number of missiles, and maybe it's skewed towards underestimating missiles because missiles are trying to avoid detection. It's as a missing value problem. There's a systematic bias in the missingness, and so so you might want to you might want to phrase this query as a unbounded query here, and that you could not do with a closed DAG, the kind of DAG that you would have underpinning a structural causal model. You would need to have an open, unbounded number of variables. I've been working on agent models. I think there's some kind of causal probabilistic programming in the setting where you might want to say reason recursively using the Bellman equation, for example. I think that, so recursion is another use case for causal probabilistic programming over causal generative modeling.
Sorry, Robert. I guess this is sort of outside the scope of this particular paper, but I'm just wondering, within the probabilistic programming language, the way you will encode causal relations is just through generation, right? You put as input to another probability distribution. You basically chain them together, and that basically encodes causality. Is that how you get causality? Because it seems to be just a whole bunch of conditional probabilities.
Yeah, so I'll explain that next.
Okay, thanks.
So so I put a little bit of let me qualify this, that the amount of programming language theory I have was kind of like working through a Haskell book once, studying a little bit of the internals of R during my PhD. So I'm going to try my best here, and please shoot me down if I sound like I don't know what I'm talking about. So in programs, objects are defined by binding variable values to names. So here we have the expression x equals foo is binding a string object to a name x. The expression y equals 2 defines an integer object by binding 2 to the name y. And then there's a order of evaluation. There's a control flow, right? So in this expression, x equals foo is evaluated before y equals 2. So in probabilistic programming, we're going to have random variables and distributions be first-class citizens. So I'm going to kind of be hand-wavy in the abstractions here because mostly because this programming language is introducing some new ways of doing this. So I don't want to be too specific, but say here coin flip represents a Bernoulli distribution. When W equals coin flip is an expression that creates a Bernoulli random variable. We still have kind of the ordering of control flow. So W equals coin flip 0.5 to X equals coin flip 0.5. So 0.5 here is the probability of heads. And then Y is a random variable whose value is a function. So the value that is assigned is a function that combines, or the data structure that is assigned is a function that combines these distributions, some coin flip distributions with X, right? So we're able to kind of define random variables as complex expressions combining the named variables that we previously evaluated earlier on in the execution. C here now is a random variable that's defined as a function of W and Y. So what does it mean to have causal dependence in a program? So we're going to derive causal dependence from the flow of evaluation during execution. So from a high level, we'll say causal dependence means, expression. We're going to say expression B. So an expression, that's something that evaluates to in code. An expression B is causally dependent on expression A if expression A must be evaluated first in order to evaluate expression B. So in order to evaluate expression B, we have to evaluate expression A first. So a random variable. So kind of making that in terms of random variables in a probabilistic programming, so a random variable B is caused by a random variable A if B's assignment expression requires A's, or in other words, B's definition requires A's assignment expression to have first been evaluated before we can assign anything to B. So in this case, X is going to be a cause of Y, and both W and Y are going to be causes of Z. Now, you might look at this and say like, well, I can kind of see an implicit graph there, right? Like there's an edge from X to Y, and there's an edge from Y and there are two edges from Y and Z to W. Sorry, from W and Y to Z. But we could do something like, if you look at, say, for example, the value of, we could add some control flow here so that, we can have an if statement so that Z is defined in terms of W or Y if the if statement evaluates to true, else Z equals coin flip 0.5. And so that kind of conditional, so in that case, W and Y would still be a cause of Z, but it would be conditional on things that happened previously in the execution. That's something you can't represent in a DAG. Another example would be, so and then of course, if you broaden recursion, it gets even hairier. So he defines here this, in this paper, this do operator. So E line, what do you call that? A slash, I guess. What's that notation called? So E,
like a pipe
bar
or something?
Pipe. Okay. E pipe do X equal X to F. So this looks a lot like Perl's do notation. But what it means is that it evaluates to the value that E would have, so this thing evaluates to the value that would have been bound to E had F been set to X when F was defined. So going beyond so if you're familiar with kind of do style notation, there is no when in those semantics here. Now we're explicitly representing the order of control flow, the order of the flow evaluation, the flow of evaluation in a program, and we're saying that okay, we have this expression that corresponds to the value that would have been bound to a named variable if another variable had its value set to something else or set to a specific value X here when that variable was first defined. And so this is kind of reminiscent of twin world counterfactuals, but now we have order of control flow kind of explicit in the definition, which is not true in the case of structural causal models, for example. And or we just have the ordering in terms of the DAG. And the ordering of the DAG is less, it doesn't map to a temporal ordering. So, but here we have steps in a control flow. We create two copies of the program, a factual execution, and a counterfactual execution, which shares some of the variables, but where others have been given alternate definitions. This line here, strategy works even if E contains a variable Y, which was defined in terms of X. So I don't really know what that means. I thought E was a name, but it says E contains a variable Y. So I guess that could mean kind of like going up to this example here, like maybe you might say that Z contains W or Y. So this strategy works even if E contains a variable Y, which is defined in terms of X.
So is that basically a parental relationship then? Is that what you mean? Is that E is the parent?
E is not a set?
I don't think it's a set. So no, I'm guessing this because this language is ambiguous, but I think it has to do with this example we had. Z can invalidate the truth of X. I think that's what that Y could, if Y is defined in terms of X. Where's Y? What is?
Aren't they
Okay,
just saying that recursion is basically allowed by saying this? Because to do X, you're actually affecting E directly, but it's also doing the counterfactual evaluation. I think they're just saying that there could be recursions here.
It is like if they were keeping like the definition of all the variables, but like in a symbolic way.
E is a lazy expression.
Yeah.
So it's not an eager value. It's a sort of it's a lazy expression like you might have in a Haskell program. So you can figure out which variables were used in the past.
I see.
And so any change to one of the variables will affect the eager evaluation of the forced evaluation of E in the obvious way.
So
kind of like a Haskell program.
So Eli, can you talk? So I remember asking the author if lazy evaluation was kind of a requirement of this abstraction. I think he said no, but it certainly seems to be a core theme of the paper. Like, what are your thoughts on that? Is the things that we're doing here, or this abstraction, these abstractions that you're defining, do they depend on lazy evaluation?
Well, it depends on analyzing the structure of the program, right? So you could do that with lazy evaluation, or you could implement it in a compiler pass that transforms the program into its counterfactual version, something like that.
Yeah. Haskell I know Haskell uses lazy evaluation. Does anybody here a Julia user? I don't think it's necessary for the definition, but it certainly seems to be useful in understanding what's going on in the paper. I haven't played with Julia before, but after this paper, I kind of want to. They also kind of make the point that, so number one is that one thing that's cool here is that, so usually when you're in kind of Perl style interventions, you set a value to a constant. Say like, all right, I'm going to intervene on the system. This is a random variable. I'm going to say, set this random variable to the value 1. You could soften that and say, I want to, say like, X comes from or say Y comes from a normal distribution. I'm going to set it to another normal distribution with a new mean. One thing that's useful here in this programming context is that you can set it to a function. And so that's new. And then that function, depending on the programming language, could be, if, for example, it was a closure and there was a whole bunch of variables determined earlier in the execution that affects what happens when the function is evaluated, then you can do all kinds of clever things. I'm not sure. So it certainly increases the expressiveness of interventions, although I don't know what you do with it. One thing I tried to try and parse this a little bit. I tried to take that pendulum example they had, and I first tried to implement it in Python using Pyro-like syntax, and I couldn't get it to work because it was, I'll show you why. So what I did is I switched to R. R gives you a lot more flexibility of things to do with expressions and non-standard evaluation. And so kind of, I don't know the familiarity of people on this call with different programming languages, but long story short, I tried to get this to look something. I tried to take this pendulum example, make it look Pythonic, failed, and then switched to R and got some interesting results, just in terms of just what it might look like. So this is the code for the pendulum example. Actually, I don't want that. thing at the bottom, so let's ignore that. Right, so I don't really understand this physics all that well, but like, what this does is it's a recursion. Does anybody remember how to get the mouse to show up on it? Let's see. Okay, there's the option button. Okay. So this is a function called sim that takes in some things and then does some operations and then does a recursion. I rewrote the function in R. So this is just this returns well, in the case of Julia, returns a linked list. In the case of R, returns a numeric vector.
Just to clarify, Robert, this is just a little Euler integrator for the equation of motion that you get from applying Newton's law to a pendulum. So
Is that all it is?
It's a little ODE solver.
Oh, it's just a little solver. Okay, so it's not actually
solving the ODE that describes the motion of the pendulum.
And so this first thing, this returns W times sine theta. That's the actual pendulum stuff, right? So I haven't looked at pendulums since 8th grade physics. So, okay, I'm assuming that. Oh, I see. So this theta PP is like this is a second derivative.
That's right. I think so.
And then we just kind of and then we have some. So G is just the gravitational constant. L is, I've already forgotten what L is. Length.
The length.
Okay. And then, all right. So then we just use a basic Euler ODE solver to generate the trajectory. Okay, that makes sense. So that's why we get a linked list. When this we get a linked list, and in case of R, we get a numeric vector. So, on the right here, on the left here is kind of his the abstractions that he makes here. So like we have these distribution objects. So U0 and UP0 correspond to uniform random variables. We can. Okay, that we don't sample here, so that's an error. But we're not sampling yet. We just we can take those random variables and plug them into the simulator, and so that gives the simulator its random initial conditions. We condition with this pipe here with an expression, and that expression is phrased in terms of a Boolean. And so it could be any kind of, what's interesting here is that you didn't need to have a named variable or some kind of named entity in a trace, for example, but rather you can just have you can just pass in an expression. So this is saying that the last value in this sequence is equal to 0.5. The intervention has similar syntax that we're gonna set the last value of the sequence equal to 0.5, and then the counterfactual is like this. So we start with, we apply the intervention. We're applying the intervention to the sequence, and we're taking that entire intervention expression and conditioning it on some evidence. So like so I like this kind of nested order of operations. It does feel kind of very intuitive in terms of the TWIML counterfactual, where we observe that the last element of the sequence is 0.5, and then we condition an intervention model on that outcome, and you know, it's and use that to get our counterfactual, and that and so that kind of corresponds with Pearl's abduction action prediction algorithm in twin world counterfactuals. So I tried trying to write something that would look Pythonic, and failed mostly because these expressions that you condition on, or that you do, or the do expression that you can, basically the expressions on the right sides of the pipe operators, I don't know of any way of doing that in Python that doesn't look hideous. So like I guess you could write a string that you could later on pass to the eval function, but you know that's a big Python no-no. But in R, which has non-standard evaluation, and then also has a pipe operator like from the tidyverse. It felt a lot more natural. The problem with R, of course, is there's no native probabilistic programming language in R that I know of. I don't know why. I've implemented one as a kind of weekend project, nothing that would scale or be useful to anybody, but more of a kind of pedagogical proof of concept. But yeah, so you could say, for example, have some uniform distribution abstraction. You could sample from it using a sample method. You could then take this sim function defined here, pass in these distribution objects. Hopefully, with operator overloading in R, you can just get the regular things to work. And then with tidyverse, you have these pipe operators. So I'm assuming that you have some kind of function called condition. So in R, of these pipe operators is kind of %, things. What you can do is, it means that you take the output of the first expression and plug it into the first argument of the second expression. So I'm assuming that there's some function called condition that takes in a random variable, and the second argument is an expression, and then using non-standard evaluation in R, you could capture that expression and then evaluate it lazily whenever you wanted to, and so which is very much in line with what you do in the tidyverse. And so so I created this kind of made up condition abstraction, this made up do abstraction, and yeah, it looks like the semantics in Julia map to R tidyverse style semantics pretty well. So
can I ask a question with that last line?
Yeah.
Would you tell me if I'm off topic, and then please skip it? But the way the counterfactual is defined on the left at the bottom, seek, pipe, do, and then the conditional. So I would guess I was expecting counterfactual to have two do operators. Was I mistaken there? It was like two. What happens if you give the treatment, given that you didn't give the treatment? Wasn't I thinking there would be two do's in here, or is this just not right?
So let's imagine then that we weren't looking at a treatment example, but we were looking at a regular exposure, like an observational study. So say, for example, this person didn't exercise, and now they're, or, all right, how about this? COVID happened, and now I put on 10 pounds, right? And the question is, how much weight would I have had COVID not happened, right? So COVID happening isn't a do, right? That's just an observed thing that happened. So COVID happened, that's an observation. My gaining weight is another observation. I'm asserting that's kind of in my model that my weight gain is a direct consequence of COVID because of the stay-at-home policy and not going to the gym and all that. And so now to set that, I need a do to kind of set COVID from happening to not happening. So the do comes in. So I have one do there, and then I fast forward that in the non-COVID universe. So the reason, so your example, the clinical example, is because if you have a treatment that's assigned, say, through randomization, like in a randomized clinical trial, then there is a do there because randomization is a type of do. But it need not be the case. And in fact, often it isn't.
Thank you.
Anyway, so I'm not sure if this semantics kind of makes sense with DR. It feels like this would evaluate, it feels like this last line is wrong because that first expression would evaluate first and then pass it into the second expression. I know we want to do the conditioning before the do. So I'm not really sure how to handle that. Maybe if I switch the order here, so if I had condition, so if I condition the sequence, patch it into a conditioning, and then pass that into the do, that's probably better. Let me just like rewrite that actually. So what I'm proposing is that this might have been a better way of writing that last part. First off, I don't want these. First off, I'll call it that. Condition. This feels awkward still, but maybe that's better. I don't know. Just, I mean, this is kind of trying to translate things between languages is kind of how I understand abstractions sometimes, but just the difficulty in making this work gives me an intuition of what might be a good way of representing this. Anyhow, going back to the paper. So, I mean, what I really think is interesting about this paper, so I've written some papers kind of reasoning and counterfactual to dynamic systems. For me to get it to work, well, I first just got it to work using Perlean style modeling, which required me to take a system that had where I knew what the analytical steady state was and cast it into a steady state model, use that as the kind of backbone of a structural causal model with all kinds of inconvenient assumptions that had to be made, and then applied Perl's counterfactual algorithm to that. And so this suggests that with the right programming abstractions, I wouldn't even have to do that. I could just have a dynamic model, one, for example, like a pendulum that has no steady state, and just kind of go in and change points. And the reason I thought that would be difficult is because, like, well, you'd have to know exactly like what time you wanted to go into the dynamic process and change things. And this avoids that by saying, no, it's just going to, rather than working in terms of time, it's going to work in terms of order of evaluation. So the implicit time that comes in the ordering of expression evaluation in a program. And they also give an example with predator-prey dynamics. So that's a computational biology model where you have, say, foxes and rabbits, and two rabbits come together, they spawn a new rabbit. A fox and a rabbit come together, you lose one rabbit, and then foxes maybe die if they don't get enough rabbits, and foxes give birth to new foxes at a slower rate than rabbits, stuff like that. And so, like that's, you know, so they use that in ecology when they're trying to kind of build a model of a complex interacting system of agents. And there's also a stochastic system as opposed usually it looks like they used differential equations here, but oftentimes people model this with the Gillespie algorithm, which is a type of stochastic differential equation. But even in that setting, you could get this to work. You would just need some random, you would just need to be able to, the random seeds that go into the random sampling of interactions between animals would have to also be made explicit in the model. Then he gives some examples towards the end in terms of counterfactual planning, like I suggested, was a very important use case. In the talk that Jeremy shared in the Slack, he talks about thinking about occlusion. So occlusion is you know, thinking in terms of but-for causation, which is a kind of counterfactual statement. Like, the reason I can't see the ball is because something is in front of it. If I remove that thing, then I would be able to see the ball. That's, so that thing is occluding the other object. So so there's a computer vision example where you can reason about what this image would look like had that object not been included by another object. And it seems to me that most of the meat of the paper is in this this calculus, this new calculus, this lambda calculus for counterfactuals that he defines. And you know, I'm still digging into that, trying to figure out. I don't think I'll be able to understand it that well because it's just not my background. But like, I'm hoping somebody else maybe can explain it to me. But what I'm hoping to, I'm going to read it a few times, and what I'm hoping to see is, you know, it's like here, like it's just something. However, by the time execution evaluates the do, y has already been bound to 0, so that rebinding x does nothing. To overcome this, we need to redefine let to use lazy evaluation. So it seems like lazy evaluation, at least in this case, is an important way to get this calculus to work. And so, yeah, my plan is to continue reading this and maybe see if I'm really trying to understand. He has some examples here of what the useful applications are. I guess my hope and my takeaways is like, all right, what do I learn in terms of programming abstraction that would allow me in? Because then I can, you know, I know that probabilistic programming is going to be more expressive than graphical models. So, you know, if I can take that expressivity and map them to specific programming abstractions, then I think I come away with something good. So far, I've learned that it's interesting to be able to, say, do Perl's counterfactual style algorithm in terms of like a series of pipes, like you have in a functional programming language or in tidyverse. And that's defining an intervention in terms of a function, which may or may not be leaky, could also be doing really interesting things. So that's what I got. Happy to hear what other people think.
I find it interesting the part that part that you mentioned, the lazy evaluation, but also with something that he discusses that he mentions in the discussions, which is the validity of interventions. I mean, because at the end you can change, you can make an intervention that completely validates the program. I don't know also about programming languages, but as far as I know, Julia you have to compile the code. But yeah. It is hard to detect when you make like an invalid intervention.
Yes.
I mean, in Python, you can just run it and break it and get an exception. Maybe you have also exceptions in Julia, but yeah, it's like if you go back, in time on that part of the execution, you will break that that trace or that execution path if you make an invalid intervention. But yeah, in order to get that, I don't know how to how would you validate that an intervention is okay with your program?
Yeah, and we have. So there's been some work on this. Let me see if I can bring it. So this, for example, so people who are familiar with dynamic models, say for example in systems biology, you might know that there'll be some, you specify a bunch of variables inside your dynamic model, but there's some kind of implicit conditions that can't be violated. Say for example, if so let's say in systems biology you might have a model of phosphorylation. And so there's a fixed amount of proteins in a cell, and they're either, and those proteins are, so a protein of one type is say either not phosphorylated or has a single phosphorylation or a double phosphorylation. So phosphorylation just means that it's enzymatically active. It can do things that it couldn't do before. But there's a fixed, and so you have three species here, or let's say just two species. You have the unphosphorylated species, and then you have the phosphorylated species. But the total amount should stay constant, putting aside things like degradation. But you could say define an intervention that says oh, well, the amount of phosphorylated protein is not 30, but it's 10, right? But then the total amount of not phosphorylated protein should increase, or otherwise you violated a constraint on this system. Similarly, in a kind of epidemiology model, those compartmental models like survival, infection, susceptible, exposed, infected, recovered. The kind of models we're using to model things like COVID spread, right? The total amount of population, so the number of susceptible people, the number of exposed people, the number of infected people, the number of recovered people, that has to stay constant, right? And unless you want to factor in death, and then you just kind of have a third variable for death, but the number of a fifth variable for death, but the number of people in the system doesn't change. They just kind of change state. So if you go into one of those variables and say okay, the numbers of infected people is this much, then you would be violating, the one of the core assumptions in the model, and then the outcome of that intervention, you wouldn't be able to interpret it correctly. So it'd be cool then if you could implement this in a language and then have that be a compile error, or yeah, your program won't compile. It would be terrible for that to become an issue at runtime. This kind of.
Can I ask a question?
Yeah.
Is this saying that to get counterfactual queries, we actually have to invent new languages? That we can't do that with existing, let's say, Pyro or something? Or is that not true? Eli have any comment on that?
So in the course, Eli will have a lot to say on this. So let me just jump in real quick. So in the course, we do explicitly model Perl-style counterfactuals using Pyro, and it's brittle. If you don't, so in other words, you can do it, and you have to specify your model correctly, and then you have to kind of find ways to make inference to work. What we'd like to do is just have really, really nice abstractions like this. Number one, that might be syntactic sugar, but also that allow you to maybe, the way I do it in the course kind of implies that you have, there's an underlying DAG. I haven't tried doing it without a DAG. But Eli, I'll let you talk about your efforts to get counterfactuals to work as a native idiom inside Pyro.
Oh, sure. Yeah, I think it wouldn't be so difficult to implement machinery like this in a language like Pyro. the trick is making sure it's compatible with all of the existing machinery for probabilistic inference. It's not there's nothing fundamental in the design of a language like Pyro or another probabilistic programming language like Stan that would
stop you from doing this.
Preclude its extension with Omega style counterfactuals.
Stan is a typed language. So you have to like, it's really hard in Stan to have things kind of change dynamically during execution, right?
Well, you might have to implement the things differently.
Yeah.
Right? You might implement a counterfactual operator as a program transformation, compiler pass. But there's no there's nothing in the such an extension wouldn't contradict anything in the design of Stan, except that, you know, people might often write their sometimes it's difficult to some models in some programs in Stan are best understood as undirected graphical models, and it's a little bit difficult to there's a bit of an impedance mismatch
with
those and with Perl style structural counterfactuals.
Can you talk like I know you looked at this paper before and you were thinking about, I think you were saying that there was a reason, I know you Slacked me some messages, I didn't get a chance to read yet, like why this wouldn't work that well or be just really hard to do in Pyro. Why is that? I was hoping you could share
that. It's just has to do with the implementation details of inference algorithms in Pyro, the way that inference algorithms work.
But you did get
to, getting back to my point about there being different implementation strategies for the kind of high-level behavior described in this paper. In Pyro, we might implement simultaneous parallel evaluation of factual and counterfactual worlds by taking a PyTorch tensor valued factual expression and a PyTorch tensor valued counterfactual expression, and stacking them, taking those two values and stacking them along a new dimension, which would effectively evaluate the rest of the program in both worlds simultaneously and in parallel. So there's nothing stopping us from doing that, but it would just have to be carefully taken into account in the way that some of the existing inference algorithms understand what certain probability distributions mean.
Could you do something like this? Could you say, for example, do an intervention? So you have a do operator in Pyro. What would you need to do to get to an intervention that was like, rather than specifying an explicitly named variable, but like rather like having some expression that says something, say for example, so I mean, I think kind of setting an intervention to the outcome of a function, that's easy in Pyro. But having something like this, like the last element of this sequence, that kind of non-standard evaluation seems to be tough to do in Python, or at least not very Pythonic.
Well, it depends on the degree of generality you'd like to achieve.
Yeah.
Set of models that you'd like to cover. The set of models that it's feasible to do inference in, do probabilistic inference is
Yeah, I mean this
one that admits simpler implementations.
Like this seems like a good use case here because it's like this sequence corresponds to the unfolding of a dynamic trajectory, and so if you just observe the last element of that sequence, so say for example if this were like a Markov decision process and you observed just the outcome of an episode, then you might want to reason about kind of how that episode unfolded, like, you know, with trying to reason counterfactually if the agent got to some kind of goal, for example. But it also feels like this is way too general. Like, there'd be a lot of it's like a great proof of concept, but like there's a lot of, it might be too general to be useful, because it would be brittle. Like to Raul's point, like you can just have a bunch of interventions that violate assumptions. Like this is actually a paper that explores that a little bit. So this is, so it's pretty abstract. So structural causal models provide a popular causal modeling framework. They're not we show that they're not flexible enough to give a complete causal representation of dynamic systems at equilibrium. Instead, we propose generalization of two notions of an SEM that we call a causal constraints model, and prove that they do capture causal semantics of such systems. And so the causal constraints, and so they have an example of a biochemical reaction with an ideal gas law. And the causal constraints is like, they basically formalize what interventions you can and can't do, and then have that formalization be part of the model. And just kind of made explicit in the model definition, and just kind of do some proofs. So there's a little bit of, so this is similar to what I just said. So this is like a enzyme reaction, substrated enzyme creates a compound creates an active version of the initial substrate. And the enzyme's still there. Like there's a certain kind of preservation of the total amount of enzyme and substrate that needs to be, and compound that needs to happen here, that you could easily violate with an intervention. Anyway, so like there is some theory behind how this would play out.
Well, I'm not familiar with that paper, but I'll just point out that one change that one might make to the design of the counterfactual operator in the Omega paper is that instead of allowing counterfactual interventions on, at any point on the program on variables at any point in the past, you might require that the intervention expressions be evaluated at the point of intervention. That allows you to avoid introducing, time travel between your factual and your counterfactual worlds, for example.
Is that, so that's not a constraint there? I mean, because it says that the intervention is like what the value that X would have had Y had been set to a different value at the time that it was named or it was defined. Is that not enough of a constraint?
Yeah, I guess it ends up working out in most cases in Omega. I think there's still some pathology there that also complicates the implementation. So if I were gonna implement something like that, I would. That's how I would change the design.
And you do have.
I would have interventions evaluated yearly rather than lazily.
I see. So you're saying like the lazy evaluation can get you in trouble?
Potentially.
And would there be any way to capture that at compile time, or would you just have to wait to execution? Some kind of something. So that could be that'd be another paper, like, you know, counterfactual validity checker.
Uh,
I know even less about compilers than I do about programming languages.
yeah, I don't know. I think one takeaway from this paper might be that it's not so obvious what in this more general setting than the setting of structural causal models, which one might think of as a strict subset of the programs described in this paper, in particular the strict subset of programs with no control flow and with static single assignment, and that is where every variable is assigned exactly once.
Sorry, say that last part again.
So for the set of programs, the set of omega programs where there's no control flow, so there's no if statements or for loops or whatever, and and the programs are in what's called static single assignment form, where every variable is assigned exactly once. So you're never changing the meaning of a variable in the course of program evaluation. You're never rebinding a variable. That subset of programs corresponds to structural causal models that Earl talks about. And in that setting, it's clear what it means for obviously we have all these definitions of what it means for things to be valid. But I would say that the definitions themselves start to break down when you introduce control flow. You have, say, recursive programs or programs with mutation or control flow. It's not clear what it means for this very general notion of a counterfactual intervention to be valid or invalid.
Yeah, I mean, that's the trade-off. Like we have, the structural causal model just has a rigorous set of math propping it up, and that all breaks down once we get rid of a DAG, basically.
Well, you can still be rigorous about this stuff in this more general setting. The point is that
nobody has yet.
The notion about the notions that you'd like to be rigorous about are no longer clear.
Yeah, I mean, and I suppose
it's maybe not clear what sorts of interventions you should allow or disallow.
Can I ask, do you sometimes explicitly model the DAG in Pyro?
So when I do, so most of the causal modeling I use Pyro because I like Pyro that treats interventions as technically they're an effect handler, but I like to think of them as a program transformation, which means that you define a function as your model, and then you kind of pass it into this do function, and it spits out a new model where the thing that you wanted intervened on is that line of code is changed, and that's an abstraction that's very close to the causal graphical model type of graph mutilation type of abstraction that underlies do calculus, and so so Pyro, what Pyro allows you to do that you can't really do in something like BN Learn is you can then kind of write functional relationships between like children and parents in a DAG that say, for example, reflect logic or physics relationships that are more complex than what you could model with like a normal conditional probability distribution. But when I use it, I typically stick with the DAG. The only time that I've deviated from a DAG is in agent models where I need agents that can reason about themselves. So I need to have some kind of way of handling self-awareness or introspection. So that's the only time I've used, and I've had, and when I was doing that in Pyro, I was kind of stretching the limits of Pyro. Although I got it to work. Just needed, for some computational hacks. But generally the answer is yes. Like Pyro gives you, and also what Pyro will allow you to do is, say, work with rich media where you want your variable to represent a tensor of pixels, for example. Most of the kind of graphical modeling approaches typically don't really, well, at least the frameworks, the software out there, they don't really allow you to model things that are not univariate. Bayesian hierarchical modeling software like Stan and Pyro, you can still have something that's like you can think of as DAG and yet have multi-dimensionality so that you can, do things like model, you can model pixels or natural language, or just basically have tensors.
So it sounds like you can do some things by treating the variables in Pyro as nodes. It seems like maybe you're kind of implying that, but maybe still the DAG is not fully modeled as a first-class object, and so maybe certain things are harder in Pyro because we don't have a first-class DAG object. Is that?
Put it another way, like, yeah, you model the things as nodes. In fact, in some of the homeworks in the workshop, like you start with a DAG that you model and be and learn, and then switch it to Pyro. Pyro doesn't force you to do that though. So if you violate, if for example you say like, Pyro would allow you to say model the number of things in the program as a Poisson distribution, while a DAG has so that's an unbounded number of discrete objects, while a DAG, the number of discrete objects is fixed. You could have control flow, you could do recursion. Those are things you can't do with the DAG. Pyro is not going to stop you from doing that. But when in the course materials I have in the workshop, for example, or in the repo, we always just assume a DAG.
Thank you.
So, I mean, I guess it's like, you have, the more expressivity you get, the easier it is to get yourself in trouble. The other thing that's nice about a DAG and a probabilistic graphical modeling framework is that inference is way easier because you can just kind of use under the hood belief propagation style inference, while once you get rid of that, then you have to use stochastic variational inference or HMC or things that work well but require you to know a little bit more about inference than you might want to, and how to get inference to work than you might want to. But again, I think because in machine learning, since we're already kind of spending a lot of time trying to get deep learning to work when the models can be quite brittle, I think that's a fair trade-off. Cool. Any other comments? Somebody has something in the chat. David, you've been quiet. Was there anything? What did you think?
I need to finish the course before I can really pass commentary. I will also take a look at Julia and Pyro. I haven't looked at them yet, so I'm confident I can grasp them. I honestly just haven't even looked. So it's a very interesting thing. I'm just trying to pick up what I can this time around. I will pause the paper and I will watch the video again when I've got a little bit more knowledge. So
also in the course materials, I have an interview with the author of this paper. So Pedro, when we start talking about causal probabilistic programming,
I'm very, very interested in this. I'm also working in the agent space. I'd love to actually have an offline conversation with you about my general approach, and you can offer some critique. That's not appropriate here. So this is right on topic for me. I really do want to learn it. I just have to climb the hill. So, yeah.
Anybody who's interested in kind of counterfactual reasoning on dynamic systems, this paper is definitely worth the read. I know I submitted a paper once on this thing, and then like I got a strong rejection from one of the reviewers, and just the language of the rejection, I knew it was one of the authors of this paper. So, and then like this paper came out very soon after that my paper got rejected. So I'm like, aha.
Which paper?
My paper, or this paper?
No, you're not sharing your screen, so I don't know.
Oh, sorry. Share screen.
So, Robert, what was your sense on the choice of, I guess, ODEs or dynamical system they picked for this paper? Like the pendulum example, I mean, it's nice and simple, and I can see why you would want to use it. But then they're sort of, for their do calculus, their intervention was changing the length of the pendulum, which seems like a really contrived example. Do you have it?
Or changing the gravitational constant?
Yeah, that's just ridiculous. Like there
must be more, I think it was literally like a Star Trek episode with Q where he changed.
Yeah, so there must be more interesting examples to actually demonstrate like how these things, how the new approach sort of gives you something.
I think I was trying to parse Julia. The abstractions of Julia are like names so that like they're impossible to Google. One second. This example here, where's the, yeah, so these examples are just toy examples. So like an intervention on the length or on the gravitational constant, like, so like, I guess what, this is like, what if we were on a different planet? Sure, but like, the example with predator-prey dynamics, that's a great example, because you would ask questions like, all right, so after observing for 10 days, we discovered the rabbit population is unsustainably high. You want to ask the counterfactual question, how would an intervention now affect the future? Had we intervened in the past, could we have avoided this situation? You know, this translates directly to a question like, had we done stay-at-home policy 2 weeks earlier, how many lives would that have saved? That's a very similar model to this one. Mm-hmm. So I think that's a much more motivating example. And also predator-prey dynamics, like, I mean, these are very standard kind of example models for dynamic systems. So it's not only a good toy problem, but it's also a meaningful toy problem. Mm-hmm. And they also have pictures here, which is interesting. And then they also have some motivating, they don't actually do examples here. So they do have some experiments with occlusion, but I couldn't actually find the code, so I don't know where this came from. So for all I know, they just drew a picture of it.
Maybe this would be maybe the COVID one would be a good hook for you to get your paper published. If you can write differential equations for COVID and run this on it, I bet you get published pretty quickly.
Yeah, folks are doing. Yeah, you're right. If anybody on the call wants to do a SIR model with interventions, I actually have a Jupyter notebook in the repo for exactly that. So I have a SIR model implemented in OpenAI Gym. So somebody who wanted to experiment with a gym in a gym environment for this kind of system using interventions, that's there for you if you wanted it.
That sounds really cool. I'll take a look.
I think I might have to merge some code. So Give me a few days. It's there. It's there if you know how to look. But if you wait a few days, then I'll reorganize the directory structure. It'll be a lot more clean. Cool.